So for these two problems, it's a straightforward prompt. Just find what are the factors of each of these two expressions, each of which is a quadratic trinomial, right? Quadratic because the highest power is the second power, and a trinomial because each has three terms added one to another. First things first, problem number 4, z squared minus 9z plus 18. How did you break apart that quadratic trinomial to discover its factors? What did you ask yourself, or what was the thought process in figuring that out? Or even just what did you get? Say again? Okay, right. So you're trying to find a number that multiplies a pair of numbers that multiply together to give you 18. And so your thought was 3 and 6. Right, so here's the thing about 3 and 6, right? If I multiply them together, I get 18. If I add them together, 3 plus 6 is going to give me positive 9. And yet I have a negative 9 here in my middle term. So how do I resolve that seeming difficulty? It seems like we're close, but our sign is off. Make what negative? Make the 3 and the 6 both negative. Exactly, because there are two ways to get a positive product. Multiply a positive by a positive, or multiply a negative by negative. Never forget both of those realms of possibility, because that's going to be the one that bails us out here. If the way that you've written it gets everything right except for the sign of that middle term, then this is always the fix. All we need to do is just turn the sign around on both the 3 and on the 6, because that will have the effect of turning those products into minus 3z and minus 6z, and yet the product of those two are still positive 18. So we haven't screwed that part up. So sure enough, when I remultiply that back out, we can always refoil in order to know that we've gotten this answer correct. We do indeed get z squared minus 9z plus 18. So cool. In fact, if we wanted to, again, kind of come up with general patterns, when this coefficient is positive, but this coefficient is negative, is it always going to be the case that I'm going to get two negatives in my factorization? If I have a pair of numbers whose product is positive but whose sum is negative? Yeah, it is the case, right? Because the only way to have a positive product is for the two numbers to have the same sign. But if two numbers have the same sign and I add them together and the result is negative, that means that both of the numbers must have been negative in the first place. The first example we did today had a negative product that had a positive middle term. And in that case, what were the signs of the two numbers? They were negative and positive, right? It was 1 and 1. And that's always going to be the case anytime we have a pair of numbers whose product is positive. After all, negative product. Negative product means that the factors had to have opposite signs. What if they were both negative? If they're both negative, it's got to be the same story. Right? Because the fact that the product is negative necessitates that they have to have opposite signs from one another. And again, as Brittany was saying, it doesn't matter which of the factors comes first. It doesn't matter if the negative one comes before the positive or vice versa. We're still going to end up in the same place. So if both of the coefficients are negative, then we're still going to have one negative, one positive in our factorization. And then the only one we didn't write up here is what if they were both positive? Then what would you expect to happen? Yeah, it's the only case we haven't seen on the screen here yet. Yep, the fact that the product needs to be positive means they have to have the same sign. And if two numbers have the same sign and their sum is positive, then that means each of the original numbers had to be positive. So you can kind of think that that's a classification of how it breaks out, if that helps you to think about what these signs do. You don't have to memorize that, but if it does help you to do so, then feel free. So that's for the first example. what changes in problems listed up here as problem number 5? What do we have to do differently when we address this trinomial? So one of the first alarm bells that should go off on this problem is that we haven't yet talked about what to do when my leading coefficient, my squared term, has something in front of it, 6y squared, right? If we tried to go at this straight ahead, the way we did the other problems, we would have to ask and answer a question that we haven't had to ask and answer yet. Because in all of our previous examples, we just had z squared here, for example. We knew that was going to be z times z. That's the only meaningful way to factor out z squared. But 6y squared, even if we know that each of those factors is going to have a y in it, now we don't know whether this is a 2y and a 3y, or maybe a 6y and a 1y, or who knows, maybe a negative 3y and a negative 2y, or a negative 6y and a negative 1y. So now there's a whole bunch more possibilities there, and when we combine those with the additional possibilities that are going to come from factoring the negative 72, now there's too many moving pieces. So really what we ought to do is make sure that there's not a way for us to reduce this problem that we don't know how to solve into a simpler one that we do. So Paula, what was your idea just then? Yeah. Get a number, factor out something to the outside of everything. Do, in other words, the first factoring method that we ever learned, which was to look for a greatest common factor among all three of these terms. Well, they definitely don't all share a y in common, but what do 6y squared minus 6y and minus 72 in fact share in common? What are they all divisible by? 6. Yep. You can find a 6 that goes into each one of those terms. So that means that we can factor that 6 out and then hope that the quadratic trinomial that we get in here in the cofactor is something that we know how to factor otherwise. So let's start by factoring out that 6. So for that, I'm just going to kind of make this little Kit Kat bar over here. 6y squared minus 6y plus 72. We've now said that we can factor a 6 out of all three of these. And so what's going to be left over? 6 goes into 6y squared how many times? 6 times what is equal to 6y squared? Y squared. Right. So the first term in my cofactor is y squared. 6 goes into minus 6y how many times? Right, minus 1y, exactly. So the middle term here is minus 1y. Great. And 6 goes into 72. Yeah, that's one that, you might use long division for, you might do whatever you like. So our cofactor here is y squared minus y plus 12. And the good news is that is a quadratic trinomial that we do know how to factor using the method we talked about today. How do we factor y squared minus y plus 12? What should my pair of numbers satisfy? In order to get to where we're going? Yeah, ready.
Y plus 4 and then y minus 3.
Let's try it.
Oh wait, no, y minus 3 and then y minus 4. Okay.
Oh, we're so perilously close here. So what do we need? We need a pair of numbers which multiply together to give me positive 12 and which add together to give me negative 1. I screwed something up.
Y is 12 positive.
Yeah, exactly. Y indeed is 12 positive. I screwed something up. I'm willing to own that. I have to be willing to own that, especially if I expect you all to own that. I need to own that. I made a copy error. Happens to the best of us. Even if it is to be avoided in general. Yeah, I screwed that up. My fault. That 12 should be negative because the 72 was negative, and when I copied it over into my little factor grid, it wasn't. Which is really good. It totally saves our bacon in this problem, and it gets us much closer to the answer that Brittany was just telling us about in the first place. So the 12 is negative. And given that 12 is negative, what's the factorization that we want in order to get the middle term to be negative 1y? Minus 4 and plus 3. Whoops. Right? Because now, positive 3 times negative 4 gives me negative 12. And positive 3 plus negative 4 gives me negative 1, which is exactly the middle coefficient that I wanted. And so, we know now that y squared minus y minus 12 factors into what? Y minus 4 from the first column there, y plus 3 from the second. And there, that is a complete factorization. So this was an example where we had to not only use the new factoring method we talked about today in the quadratic trinomial case, but in order to even get to that stage, in order to access that technique, we first had to think about the greatest common factor. And that, by the way, is sound strategy for all factoring problems. The first thing on your mind should be greatest common factoring. The first thing on your mind should be the first thing we learned this semester. And only after that method is exhausted, so after we've done all the GCF factoring that we can do, then is the time to start thinking about the more fancy techniques that we're starting to learn today. Right? Quadratic trinomial factoring we can use after the GCF has all done its work.